All right, ladies and gentlemen, your class recording for today has begun. So, yesterday, we introduced the concept, the idea of calorimetry. So the fact that it starts off with cala, right? Most of you are probably familiar with the concept of calories before, right? You've talked about that. We talked about it in terms of food, right? But a calorie is a unit of energy, okay? Calorimetry is the study of heat energy, especially, and the transfer of that energy and the measurement of it. So that's where we're headed today. Yesterday, we talked a lot about the specific heat of a material. And we talked about that the specific heat of a material is a measure of how hard or easy it is to raise the temperature of that material. Materials that have lower specific heat values heat up rather quickly, but materials that have higher specific heat values take a while to heat up or cool down. So we're going to measure that a little bit today. Did we get to the equation at the end of the class? Okay, so now that we know, we talked about in the beginning of this unit, or this part of the unit, that energy flows from hot things to cold things spontaneously, blah, blah, blah. Today, we want to take some measurements and actually figure out, okay, how much energy is flowing from this hot thing to this cold thing. And we use this equation to take the measurements and then ultimately figure out how much energy is flowing. So Q is equal to M times C times delta T. And yesterday we talked about that Q in that equation. Q is the amount of energy that is transferring from one object to another. It's the heat energy. It's measured in joules. M stands for the mass. It's going to be measured in grams. C is the specific heat value. Like I said, that's a known value. It will be given to you. Or you're going to make measurements and figure out what it actually is. And that's what you're going to do today. And then the delta T, and I think at the end we kind of like did we finish all this, or did we talk about delta T? So delta T, right? The triangle there is the Greek letter delta. That's capital delta. There's lowercase delta too that shows up sometimes. So the capital delta represents change. When in math class or in science class, we use it to represent the change in something. So delta T is the change in temperature. And to calculate the change in something, you need to know two things. You need to know where it started and where it finished, and you look at the difference between them. And we'll see a little bit more later on, it's kind of important that we go final minus initial. So where did it end up versus ultimately where did it end up ultimately versus where it started? Okay? Good there? The measurements that we make to figure out the amount of energy that is gained or lost in a situation is done using an instrument that is called a calorimeter. So, the calorimeter is an instrument used to measure changes in thermal energy. So today, that's what we're going to do. We're going to use a calorimeter to measure the changes in thermal energy. The calorimeter works on the concept of conservation of energy. Energy flows from hot things to cold things until they are the same temperature. In theory, the amount of energy that flows out of the hot thing is equal to the amount of energy that is gained by the cold thing. They will stop transferring energy when they are the same temperature. Do we remember what we call that when they reach the same temperature? What type of equilibrium specifically? It is thermal equilibrium. Okay? All right, good there? We'll finish. I'm waiting for people to finish writing it down. All right, so let's take a look at a calorimeter. The calorimeter that you guys are going to use today is not as complex as this one, but it'll do the same job. So, start off. Your calorimeter should be a fairly well insulated material because we want to focus on the energy transfer inside, not heat that comes in from the outside. So we're going to start off, and we're going to put something hot and put something cold in the calorimeter. And then they're going to trade energy until they reach the same temperature. So we start off with something hot. It could be a reaction. In the case of our lab today, it's going to be a hot piece of metal. So those pots that are sitting over there that are boiling, they have water in them. The water's boiling, and in the water there are fishing line sinkers, and they are heating up because they're sitting in the hot water. Also, in the calorimeter, you're going to have something cold. That's going to be water. So you're going to put water in first, then you're going to put the hot thing in. If the water's cold and the hot thing is hot, energy is going to flow from the hot thing into the cold thing until they reach the same temperature. All right? Based on the measurements that we're then going to take, insulation to prevent the outside heat from coming in, because we want to focus just on the hot and the cold parts that are trading energy. Okay? Using the idea of conservation, right? The energy lost by one thing has to be equal to the energy gained by the other thing. We can figure out how much energy is traded inside the calorimeter. Okay? Good there? All right. On the back of your outline, there are a couple of examples, sample calculations of something similar to what we're going to do in the lab today. So, let's run through a couple of these, just so we have an idea of where we're going and how we're going to get there. So, to measure the energy that is gained or lost in this situation, right? Q is equal to M times C times delta T. Okay? Delta T represents one quantity, right? The change in the energy. So, it says here, an iron skillet, right? An iron frying pan, if you want to look at it that way, has a mass of 500 grams. The specific heat of iron is 0.449 joules per grams per degree C. How much heat energy must be absorbed to raise the temperature of the skillet by 95 degrees Celsius? So, you do not have to do this problem my way, but I want to go through it in an orderly fashion to make sure that we're getting there. If you see it and you can plug stuff in, it's good to go, fine, but let's go through this step by step. So, we read this problem. First thing we should do as far as solving a problem goes is what? Where should we start? Say again? Nope, let's go somewhere else before that. What? What are we looking for, right? So, my example that I use for that is Google Earth, right? Google Earth, in theory, has a picture of every place on the planet Earth, right? But the first thing you have to do when you use Google Earth is what? What are you searching for, right? I can show you a picture of anything, but if I don't know what you want to see, I'm not that much help to you, right? So, if we read this problem, right, what is this question asking us for? Sure. How much heat energy must be absorbed, right? Noor, in the equation that we use to calculate these things, which variable is representing heat energy? The Q, right? So, Q is our question mark. That's our unknown value in this problem, right? All right. Now that we know what we're looking for, where should we go next? What we know, right? What's one thing that we know, Christine?
The mass of the iron skillet.
Okay, so mass of 500 grams, right? So M is equal to 500 grams, okay? What else did they give us to work with in this problem? They gave us, now, Noor, this temperature here, what is it telling you about the temperature here? Does it tell you how hot the skillet was to begin with? No. Does it tell you how hot it is at the end? If it's saying that it's raising the temperature by 95 degrees, right? That's not telling you how hot it was at the beginning, and it's not telling you how hot it was at the end. It's telling you the what? It's telling you the change, right? How hot does it go up? That is represented by the delta T. So in this case here, they gave you the change in the energy, or the change in the temperature, right, as delta T. Okay? And then, one more thing they gave us to work with in this problem. What else? Specific heat of iron is 0.449, right? So that's the C value. C representing the specific heat in this equation, right? And then joules. Now this unit is written kind of weird. I would write it like this as a fraction with joules on the top and then grams times degrees C on the bottom. Okay? Good there. Okay? So Q is equal to M times C times delta T. So now we start plugging in things that we know, right? We don't know Q, that's our unknown. They told us that the mass was 500 grams. They told us that the specific heat was 0.449 joules, grams degrees C, and then it told us that the change in temperature was 95 degrees. So, first, units, right? This unit here is a fraction, so we have some units on the top, some units in the numerator, and then some units in the denominator, right? Grams here, right? But here, grams is on the top of the fraction, if we think of that as a fraction over 1, right? And here, grams is in the bottom, so what's going to happen to grams in that equation? They're going to cancel out, right? So grams cancels, right? And then delta C, degrees C, right? So the only unit that we're left with is what? Joules. And that's good, because what are we trying to find? Energy, right? Maura, go ahead.
Couldn't you just you wouldn't even have to do the canceling, because looking at it, you know that you just need joules.
Well, that's true, although Maura, the equation should show us that, right? The equation should come out that joules is the only unit because we're trying to find energy. You know what I'm saying? So yes, you can make that assumption, but the math should back that up, right? So I just want to show you that it really does, right? And then mathematically, what are we doing here to these numbers? Multiplying, right? So I think several of you have already run it through your calculator. Right? What do you get when you?
2020. What?
21,327.
Never
I
mind.
saw your thing. I was like, oh, I'm not gonna correct.
Why didn't you tell me?
I don't know.
Okay.
I'm gonna let
You
make
wanted
your
me
own
to publicly embarrass myself.
Maura, we're all friends with this, you know.
No, I'm not.
All right, maybe not. So, but anyway. All right.
21327.5.
Good. Whoa.
What the?
Ow! Don't.
All right. So, to finish this off, right? We already established that the unit on this is joules, right? But here, should we leave it as this number here? Well, we should round a little bit, right? So this number, right? One certain, one uncertain digit. Here, two certain, one uncertain. Here, we'll call this two certain and one uncertain, even though it's really not, right? But we'll call
I
it
don't
that.
understand the certain and uncertain stuff.
Say again? Because the 0 at the beginning doesn't count, right? It's just showing you that it's a small number. And that means that when we were measuring this, right, remember there's only one uncertain digit in every measurement, right? So all the other ones have to be certain, right? The last one is the one you guess on. The other ones had to come from whatever it was we were using to measure, right? So this one has one uncertain and one certain, one uncertain, two certain, one uncertain, and then two certain, one uncertain. Okay? But when we're rounding, we always go where? Least or most? Least, right? So that means here, we should probably round this answer to what?
21,000.
21,000. Right? We can't get rid of all those extra numbers, but we just got to make them zeros because we're not really sure what they are. Okay. Good there? Good, okay.
Would you take points off?
No, if you don't round it at this point, no. Okay. I keep telling you that eventually I'll teach you the rules, and I will eventually. So when I don't know, but I will. So. All right, good there. All right. outline, there is problem number B, or problem letter B. All right, so let's take a look at that. This one is a little bit harder. You have to pick out a little bit more information in this problem. So, we read the problem, right? 1 kilogram, which is 1,000 grams, of frozen water at -5 degrees Celsius is placed on the stove. Water, as a solid or a liquid, has a specific heat of 4.18 joules per gram per degree C. How much heat is required to bring the water to a boil? So starting off, right, what's the first thing we should do? What are we looking for? So Noor, what are we looking for in this problem? How much heat, right? And what letter do we use to represent how much heat, Noor? Q, right? So again, this problem is asking us about Q. Okay. Next, things we know. Sorry, I guess I should point this out, right? If you guys can do this without doing it my way, that's fine, all right? But I want to make sure I'm showing you at least a comprehensive and detailed way of getting through it, okay? All right, so things we know. Julian, you have your hand up. What's one thing we know here?
Yeah, 1,000 grams.
Okay, so 1,000 grams, that's going to be our what? That's going to be our mass, right? So mass is 1,000 grams. Okay, what else did they give us to work with here? Say again? The specific heat of water, right? Water has a specific heat of 4.18. Okay. Before we go on to the next part, what do you notice about that specific heat compared to the specific heat of the iron in the last problem? Significantly higher, right? Remember yesterday we talked about that water has a very high specific heat value. That number, 4.18 joules per gram per degree C, you're going to need that today when you do your lab. So keep that in mind as we go forward here, okay? All right, next, what else did they give us to work with?
What it started at and what it needs to end at.
Okay, so we know this, right? So Maura, what is that going to be? What variable is that going to be?
That's gonna be the initial
Good. The initial.
initial temperature.
Right. So that is Ti, right? The initial temperature is -5 degrees Celsius. All right. What does it say ultimately happens to the water in this example? Maura, go ahead.
It boils.
It
so
boils, right?
It
So
would be 100 degrees Celsius.
that means that what's going to be 100 degrees
T,
Celsius? T final will be 100 degrees Celsius. Okay? Now, do either of those numbers go in our equation? No. We don't want the final temperature. We don't want the initial temperature. We want the change in the temperature. Now, looking at this, you could probably figure out pretty quickly that the change in the temperature is going to be what? 105, okay? But, like we talked about before, the math needs to support that, right? So, when we calculate the change in temperature of something, when we calculate the change in anything, we always go T final minus T initial, or whatever we ended up with, minus where we started, okay? Like I said, I know that most of you could probably figure out that delta T is 105, but let's keep in mind that the math has to support that, okay? So, we start plugging in things that we know here, right? We said that the final temperature here has to be 100. Then we subtract the initial temperature. You can't change the formula. All you can do is plug things in. So we subtract the initial temperature. But what was the initial temperature in this problem? -5, right? So mathematically, what do we end up doing here? Adding, because we're subtracting a negative, right? So the temperature change does turn out to be 105 degrees Celsius, right? But because we have to subtract, okay? So when we plug these things in, right? Q is equal to M times C times delta T, right? That means Q is equal to 1,000 grams times 4.18 joules per gram per degree C, that's a J, times the change in temperature, which is 105 degrees C, right? Again, grams, delta C, degrees C. You run that through your calculator and you get 438.
900.
Is it 438?
900.
900. Okay, that's going to be joules, right? But from a rounding standpoint, right? 2 certain, 1 uncertain. 2 certain, 1 uncertain. If you go back to the original problem, yeah, we plugged in 1,000 grams, but really they gave us 1.0 kilograms, right? So that's only 1 certain and 1 uncertain, right? So here, we should probably round this to what?
440,000.
440,000.
How does that happen? It's because one certain.
It's because there's the one certain is the 4.
Nor does that make sense why it's 440.
But then 4.
See, it's working.
Because you got to use the 1 certain,
the
1
next
uncertain
one
in
is
the beginning.
So you round up to 400.
All right.
The rest is just placeholder.
Okay.
Good there? Okay. These calculations are very similar to the calculations that you're going to have to do in your lab today. Right? Again, I said make sure you keep in mind the specific heat of water. Right? You're going to need that value. Oh, one last thing. Hold on, freeze. This is kind of important. In the case of this water, physically, what was happening to the water in this example that we just did? What were we doing to it? We're adding heat to it, right? And Trey, ultimately, we got it to do what? Boil, right? And that meant that our change in temperature, right, was positive. But if something cools down, right, its final temperature would be lower than its initial temperature, right? If something cools down, it gets to a smaller number. So when you go to do delta T, you're going to end up with what? A negative number. That's okay. That happens, all right? We have to make sure we account for what we're actually recording, though. Okay? Good there. All right. Let's take a look at your lab. Oh, Maura, were you supposed to remind me of something?
Oh, yeah. Turn it off.